let's talk about the estimation problem of regime switching model. First, what I brought here is some histogram. And if you look at this histogram closely, it appears to be asymmetric, right? So it has longer tail, right? Then what would be this distribution? Okay. Suppose you have a data and you draw this type of histogram and you found this shape. And you try to find a right distribution that explains this data. Have you seen such distribution before? Doesn't look like normal, right? Doesn't look like t. Doesn't look like chi-squared, right? Chi-squared has a density function that is located to the right of this origin, okay? Always positive. So none of them appears to be explaining this one, okay? But what I did here, well, it appears that this curve closely explains histogram, right? The way I draw this graph is, suppose I have normal distribution having mean mean here, negative, right? And big variance. And I have another normal distribution, a little bit truncated here, but if you see it, right about here, the second one, okay? And there's another normal distribution where you start from here, and there's a peak somewhere, and then, yeah. Okay. If I assign some weights to these three normal distribution, then I can make this curve. So it's like you can create some color by mixing red, white, blue, or green. So if you add those three elements of color, then by mixing it, you can create, very nice colors, right? Variety of colors. So it is the same situation. Actually, the way I draw those numbers that yielded this histogram is I draw some number, standard normal distribution from standard normal distribution, and I square it. So if you square this one, then this is chi-square random variable, right? And then I take natural log of that. So I draw 10,000 of this random variate, and I draw that distribution. So the distribution of this, as you saw there, has shape like this, right? Because when you have chi-square distribution, you'll have a shape to the right, right? But by taking natural log, it is the other way around, right? So in this case, I know exactly what is the underlying distribution. But in general, if we are given some numbers, like distribution of, let's say, GDP growth rate, it may or may not look like normal, right? But we suspect that this might be the case. The reason being, we say, sometimes you see most of the mass lies here, right, in this area. And then some here and a little, right? So you can think of this as, let's say, there is some state when you have high mean and smaller variance. And there could be some state with low mean and smaller variance. Maybe some crisis period, you have very small mean growth rate of GDP, but could be wide. Right? So our task is to introduce some econometric model, time series model, so that we can, hopefully, we can identify whether there are different states, 1, 2 state or 3 states, and their parameters. Okay. So the model we've seen last time has that nature. See, if current state is, let's say, 1, then this is mean, right? This is mean. So that's the center of distribution. Mean, and this is the same thing. So the variance of x is sigma squared, right? Like that. If state is 0, then this is the mean, right? So it could be mean here, and then same normal distribution. Right? The mixture normal model doesn't say much about the way state evolves over time. So ST could be purely random variable, independent random variable. Or it could be like, state-dependent variable. The regime switching model will be examining has more feature like this. Let me get back to this one shortly. But let me show you this. I have 10,000 observations to draw this histogram. That's what I said, right? So I have first number drawn, second number drawn, and all the way up to 10,000. Right? The first number, when I see that, can you guess what would be the probability that particular observation, the first observation, is drawn from this distribution, or this distribution, or this distribution? And somehow, if we can tell that, it will be nice, right? Actually, this is the plot of that probability, the first 500 observations. So this is 0, and this is about 80%. So the particular observation should belong to either this distribution or this or that, right? 1 out of 3 chance. But what is the probability? It says the first one, for instance, let's say it is 70%. Probability that the first observation belongs to the first this first normal distribution is about 70%, and let's say the same probability, but for the second state could be 20%, and the probability that belongs to third state could be 10%. Then what would be your conclusion? 70%, 20%, 10%, adding up to 100%, right? Then you might say, well, it is drawn from first distribution, right? So our method is actually exactly doing that task. So in somehow you need to calculate this kind of probability, right? One way to calculate those probabilities is to use a well-known theorem known as Bayes' theorem. So Bayes' theorem is a basic tool when you try to analyze this kind of probability. Okay, so we'll get to that part. A little more about the structure. Well, regime switching model could be more complicated than this simple specification. For instance, you could have state 1 or 0, or it could be 1, 2, 3, 3 states, or 1, 2, 3, 4 states, right? If you prefer. So you can have more states in this dimension. And also, in this case, mean is shifting. But this could be also state dependent. Right? And also, there could be some serial correlation going on here. Okay? When James Hamilton introduced this model around 1987, I believe, he tried to model U.S. GNP, gross national product, and considering this one as GNP growth rate, and structure is the same, but he introduced here autoregressive process of epsilon t, and the order was 4. Because GNP or GDP are published every quarter, so this is quarterly data, and accidentally found some serial correlation of lags up to 4, and he assumed this one is constant. And then he estimated a model and calculated the probability that the current state belongs to either 1 or 0. Okay. But when he considered that kind of a scheme, this is the assumption about random variable S of t. Now, what it says is it is dependent, right? Dependent. So this is a probability. So what is the probability of current state being 1 when previously in the same state 1? So this is the probability of staying in the same state 1, right? And let's say that is p, some number, 90%, some number. This is the number we'll try to estimate from the data. Okay. Similarly, when we assume just 2 states, in this case 0 and 1, and staying in the same state 0, it could be q. Okay. Then what is the probability that it switch from 1 to 0? 1 minus p, right? 0 to 1, 1 minus q, right? So there are 4 possibilities, right? 1, 0, staying, switch, staying, switch. Okay. So in somehow, we are at t, and we don't know whether we came from this path, or this path, or this path, or this path. So we have to consider 4 possibilities, right? 4 possibilities. So when you calculate probability, you can think of, let's say, probability that current state is, let's say, 1, conditional on all the information available up to t. we can think of this concept, right? We can think of this one using information set up to previous period. So this is the kind of prediction, right? T minus 1 T, and this one is update, right? So it involves Bayes' theorem tell you how to update your constants about certain event. Let's say you are interested in whether current state is 1. Probably you make a guess, and then the difference between these two is whether you saw this number or not, right? This one is not included in this information set, right? But this one is included here, right? So without seeing this one, just using information all the way up to here, you make a best guess, and then in somehow, when you receive new information, you try to update the forecast. So if you can do that systematically, then you are close being to handle this type of estimation problem. So let's take a look at a little bit more about this. So here, the number of parameters we are interested in, we need to estimate in this simplest case, beta 0, beta 1, sigma squared, P, and Q. Right? One of the probability, the property of ST we assume in this kind of literature is ST has so-called Markovian property, which means when you talk about this probability, all you need to know is the information or the state in the previous period. Of course, we came to, let's say, this state following some path, right? And other path, right? But if you start from time 1 to up to some future date, there are too many possibilities, right? So quickly you can't count, you can't model all those possibilities. Right? So it's like, this case is, we have 2 states and 2 possibilities, so this is number of cases. And then 3, and T, and if T is 100, the computer will say, well, it's not my business. I can't handle it, right? So the Markovian property we use in this estimation is when you handle this problem, the current state here, we worry about just previous period, this one. When estimation is done, this is the one. Because this is a random variable, right? We can, of course, calculate expected value. And this is not a conditional expectation. So if someone calculated this one and got this answer, then what it says is this is the probability that current state is 1 unconditionally. Of course, 1 minus that has to be this one, right? So the reason I brought this one is in somehow when we do the iterative calculation, we need to start from somewhere. So this has something to do with initialization of the problem. Okay? And expected duration, because, well, suppose that this probability is 0 and this probability is 1. then there is only one state, right? State 1, right? Doesn't switch. But by having some positive numbers, what that means is once you enter some particular state, there is a tendency to stay there in that state for some extended time. Right? So it's not going like state 0 to state 1 to 0. It's not bouncing. It's like it's moving this way and then switch and then stay and switch and then stay. So that kind of structure. Right? So once you enter in either state 1 or 0, you can calculate expected number of duration. So when you have quarterly data, you can calculate, let's say, the duration is 3.5. So 3 quarters and 1.5 months when you are in recession. That kind of a statement can be made using this one. Okay. This is Bayes' theorem. Applied to this particular problem. It may look awful, but when we actually tried this estimation, then that's not as horrible as it appears to be. So what we got here, well, before I do that, why we need to worry about particular probability associated with this path, or this path, or that. When we go back to our maximum likely estimation of simple problem, this is the one, right? Then we think about likelihood function at time t. As square root 2 pi sigma So if you have some initial guess on these two parameters, and because you assume normal distribution, so this is normal distribution, right? What is epsilon? Of course, epsilon t is xt minus beta, right? Xt minus beta, right? So given this guess, so these are known. This is theta. Functional form is known. So you can calculate likelihood value. Right? We typically calculate natural log of LT. This one. Right? You sum it over up to cap t. And you want to maximize this one with respect to this parameter, right? So that was maximum likely estimation. Now key is this one. Now problem. See? When you try to calculate likelihood function at time t, if beta depends on state. Okay, so beta st is, let's say, beta 0, 1 minus st, beta 1 st. Then how to compute this one? How to compute this one? xt minus something, right? Which one? Which one? We don't know, right? We don't know. So you are guessing. Let's say it came from this path, 1, and it stayed. So 1, in this case, then beta 1, right? So you calculate here epsilon t as xt minus beta 1. What if this is the case? Well, in this case, xt minus beta 0, right? In this case, it's 1, right? Epsilon t, xt minus beta 1, epsilon t, xt minus beta 0, right? So you plug in there. You plug in there. So what that means is we have 4 log likelihood values at t, right? Corresponding to these possibilities. We try to maximize this thing somehow, right? But at time t, we have 4 of them. So how to make it 1 to maximize? Well, if you know in somehow probability at time s at t is 1, so this probability, let's say that is 0.70, 0.10, 0.10, 0.10. Suppose you calculate that probability. Then, likelihood function could be calculated as 1 by weighting those likelihood values from each calculation by this weight. Right? So more likely one has more weight, less likely have less weights. So that's the idea. Right? So we didn't have any problem here because there's only one likelihood value at t. But our problem, we have 4 of them, so we need this weighting scheme, right? So calculating these numbers are critical, right? So we'll try to do that using Bayes' theorem. Okay. So let's take a look at this formula. Basically, first of all, this expression looks awful, but this is same as this one. This one. So what it says is basically we have number of variables 1, so this has to be I believe this one has to be 1. Yeah, same. And somehow I borrowed this one from a multivariate case, but in a single variable case, n is set to 1. So basically, this is log likelihood function or density function of y when those informations are given. Okay, but here what we are really interested in is what is the probability that probability of observing these two at the same time. So here, if it is 1, 1, 1, 1, this guy, right? 1, 1. That probability is 1. 1, 0, 0, 1, 0, 0. Right? So 4 numbers using information up to this. And then how to calculate this one? Well, in this way. Here, the probability of Y, conditional information set, and the same information set on the right-hand side, and the joint probability of observing the state and the data. But if you look at this part, it would be much easier to understand. Okay, here what it says is this is the predicted probability of observing this sequence using information set t-1. So very similar to this one, except the information set, right? Then what is this guy? What is this guy? Here. What it says is, and somehow, if you know, if you have probability of state S in the previous period is I, using that information. Suppose you know this number. Suppose you know this number, then the probability that you observe this sequence can be computed by multiplying from this state to that state. See? You start from here, given that, you move to there, right? So that's the joint probability. Right? But we know this is very familiar, right? This is very familiar. If it is 1, 1, that is P in our previous notation. If it is 0, 0, then that probability is Q. Right? So you start from here. This could be either P or Q or 1 minus P or 1 minus Q. So if this is 1 and this is 0, 1, 0, just switching, right? So in that case, this probability times 1 minus P. The transition probability from here to there is 1 minus P. This was P. This was 1 minus Q. This was Q. Right? So we understand this part, how to calculate this part. If we know this, then this part could be one of these 4 possibilities, right? So you get this number, you plug in right here, okay? And then what is this one? What is this? Well, this is calculated here as our from our normal density function, right? And this part. But actually, as I said, we are considering 4 possibilities here. In the numerator, when you have, there are 4 numbers. 1, 0, 0, 1, the 4 possibilities. This probability consists of 4 numbers, right? So this part times that part will have 4 possibilities. 4 possibilities. Denominator is simply the sum of those 4 possibilities. So later I will show you from the program what it means. And this problem has very simple, it turns out to be simple, likelihood function, which is if you calculate this one recursively, and then you can obtain objective function as a natural log of that. So you maximize this quantity. So formula appears to be awful, but let me quickly show you how to implement this one. But here, when you have this probability, we have 4 possibilities, right? This number, there are 4 possibilities, so 4 probabilities, right? You are interested in calculating this number, where you have no this, right? So when we write this summation sign from 0 to 1 for I, well, what is the probability at time t, the state being 1? What would that be? This plus that, right? 1, 1. Whether you stayed or switched, this is the probability at time t, the state being 1, right? So sum of these 2. That's this notation. Okay. So you get this number, and in the next iteration, t, right? t plus 1. So you can go on, right? Okay. Then let's take a look at this Gauss code. First, this one. This is the code I borrowed from someone else, where it creates sequence of 1s and 0s. Where, well, this is number of observations, so 100 observations. ST sequence. A0 is a switching probability from 1 to 0. Oh, sorry. 0 to 1, 0 to 1, 0, 1. And this one is 1, 0, right? So switching probability. Okay. So the probability of state being 0 when previous state was 0 is 90%. sorry, 80%, right? And staying, you have 90%, right? So we set these two parameters and number of observations, and then you plug in these two numbers. Don't worry about this part and this one. Then it will create ST sequence. Okay. And here, the beta 0 is set to 0.5. Beta 1 is 1.5, and sigma is 0.25. Okay. So what I'm trying to do is to generate data y. So I declare this one. When you have this curly braces like this one, y is defined but not assigned any value yet. Okay, so it's there in the memory with no value. Okay, and then I iterate this loop up to 100. I have ST sequence state, and if state is 0, then I'm stacking downward y, this one, okay, where I pick beta 0 as a mean, and this is standard random normal function. So I draw one single number from standard normal. And I multiply that by 0.25 standard deviation, then this one will have standard deviation 0.25, and this y will have a variance 0.25 squared. Okay. Else, y is calculated in this way. Of course, if it is not 0, then it has to be 1. So I pick beta 1 and this one. Okay. And then I try to draw this one. Actually, procedure that draws this ST is a little tricky, but don't worry about this one. So first, this is sequence of zeros and ones, 100 of them. Right? You see it? Stayed, switched, and switched again, and stayed, switched, stayed, switched, stayed, and switched. This particular realization. So if state happened to be 0, we have mean value beta 0. If state happened to be 1, then you have mean beta 1, right? So it's switching this way, okay? Ones, zeros, ones, zeros, right? Oh, sorry. So try to remember this. Well, there are periods where you observe more of the same state here, right? And let's compare that. With this one. See, high mean state, low mean state. But we know that there are several switch, right? But you actually observe this as a data. Often you don't observe underlying ST. Right? So we'd like to estimate what would be this high growth, the mean value for this high growth state, and perhaps some, lower mean value for this state. Or you may want to know whether in fact there are two states or the single state. Right? Like this one. So a long time ago, I asked my class to write some simple code. Let me show you this one first. Oh, that's not it. That's different. So in this program, all the way up to here are the same, just data generating process. Okay, so it generates the same data. Seeing that. We have number variable 1. This is the vector that will store this number at t. So at t, you will save the sum of this probability and that probability. Okay? And currently, I have 100 of them. So 100 by 1, vector of zeros. But as I calculate those numbers, I plug it in, those numbers, right? Okay. How many parameters to be estimated? This is P00, probability of staying in the same state, same state 1, and those are beta parameters. Sigma was 0.25, right? So my initial guess on this one, beta 0 is 0. Initial guess on beta 1 is 1. Initial guess on the sigma is 0.4. But these probabilities, we know that this number should be close to being 0.8. This number should be close to being 0.9. But these are probabilities, right? So I try to add some constraint. So whenever you receive these unconstrained parameters, the resulting output from transformation leads that value to something bounded from 0 to 1. 0 to 1. Okay? This one. So 5-parameter problem. So if you write likelihood function with that name, then you will get this converging estimate. Okay? So, well, as usual, these parts I just copied and pasted. Okay. This part is a little bit tricky, so let me show you likelihood function. This one. When we estimated a much simpler problem without this kind of state dependency, likelihood function was very simple, several lines, right? But this time we need to calculate those probabilities, so it's a little bit more than that. So when you receive initial guess, then we will transform it. And so this is a transformed parameter. Okay? 5 numbers. I call the first number as QPR, so probability of staying in the state 0. When I receive second number from here, then I call it P probability, PPR, which corresponds to this one. Okay? And third, fourth, fifth, beta 0, beta 1, and sigma squared by squaring this one. Okay. This is the probability that current state is 1. I'm sorry, not that one. You see? In this whole calculation, you have to start in somehow from this one, right? Suppose you are at time t equals to 1. Then this is 0 and 0, right? So we don't have any information. So our assumption is, let's say, we assume that state at time 0 is 1. And this is the expected value, right? So this number. So we'll start from this one. If you prefer, you can assume that current state, starting state could be this one. Right? So in either way, you should walk. So I chose this one. So I assume that at time 0, state was 1. State was 1. In terms of program, that is to calculate this one. And this notation is same as this one. This notation. So let me go back and forth several times. Of course, 1 minus that, this number, could be probability of state being 0. 0. Right? We'll try to calculate numbers up to time t equals to 100. So first, I calculate epsilon. So in this notation, this is previous state, this is current state. So 0, 0. So 0, 0, this case. 0, 1, so 1. 1, 0, 0, right? So 4 cases. So this part is done, right? It looks complicated, but it's not that complicated. This is the probability of previous state being 0, right? So next state, well, this is the probability of staying in the same state 0, right? So 0, 0, right? 0, 0. So you plug this number, and we have initial guess on this one, and we calculated this, And we have initial guess on this number, and this is normal density. That will give you this number. Previously stated 1, switch, 1, switch, 1, switch. 0, switch, 0, switch, 0, switch. 0, 0, 1, 1, so 1, 1. Right? So this is 4 numbers in the numerator in the first expression, long expression. And denominator is simply the sum of these 4 numbers. Okay. And likelihood value is, this is log likelihood value. Log likelihood value. And we multiply -1, and we try to minimize this number. So these 4 numbers corresponds to those, right? 4. So how to get this single number? So we add this and add that, right? So what we do is we take the ratio. So this is the sum, right? This is sum of these 4, right? And what we do here is to take ratio of this, right? So what I'm saying is we try to calculate weight, attach it to these 4 cases, right? So how to calculate that weight? Numerator divided by sum. Numerator divided by sum. Right? So those are 4 cases. Right? And the reason why I keeping those zeros and ones is it's easy to calculate. Say, what is the probability of state being, let's say 1? 1 is from 0 to 1, 1 to 1. Right? So adding these 2 numbers. Right? 0 to 1, 1 to 1. So that's 1. And current state being 0, from 1 to 0, 0 to 0. Right? So you have that number, that number. And I chose to keep this one in this vector. Okay? And I keep adding this one and try to minimize it. Okay? So when you calculate this PROB 0 and 1, in the next iteration, t equals to t plus 1, we go all the way up to here. Right? Here. We calculate this one at t equals 2. We know this number, right? We calculate in the previous period. We calculate this and do that again and calculate new probability and then plug in there and we can iterate this one. Right? In the meantime, we calculate likelihood value in this fashion. So likelihood value is actually this part. Log likelihood value. So likelihood value is simply the sum of these 4 possibilities. Right? So when you think of this part, when you calculate this part, obviously sum of these 4, right? Sum of these 4. Well, this is basically a normal density function, right? Normal density function. It has same sigma squared, but different epsilons, right? But those are weighted differently, right? So these four numbers are weighted and averaged. That's your likelihood function. Get the idea? We usually have only one of these if our problem was this one, right? But because we have different cases, so we have weighted average as a likelihood function. Okay? Okay. And if we run this program, oh, sorry, try it again. Okay, let's see. The graphs are PO. So 1 minus ST. ST is just 0 or 1, right? So you can show it as ST or 1 minus ST, right? And this is the predicted probability. Updated probability, this one. We call it filtered probability, this one. But as I mentioned in Kalman filter, we can also calculate this one when you have whole sample. So if you can calculate this one has more information than that because information set is bigger, right? So I calculated this one, and this is in program denoted as B post. But this one is a little more complicated. But let's see the result. Looking better? Okay. So state was this green one is actual one, 0 and 1, 1, 1, 1, 1, 1, and switched 0 this way. This cyan color, I believe that is of this case. So there is a little bit of missing, but it quickly go up and stop. Right? So think of 50% as rough decision point. So more than 50%, we call it as state 1, and otherwise 0. Okay? Well, there was a one jump and then switched back. Obviously, it doesn't find the evidence, right? Oh, actually, there is a dotted line. Oh, sorry, this is correct. This is, the light color is this part. And it finds something, but actually state was 0, right? State was 0. So probably there may be some small negative, big negative epsilon. So model may be confused a little. That as, might be different state, right? But, because this is very marginal, right? And there's a long period of same state, right? So probability increases and decreases, but quickly that, right? So why we are missing this episode? Because there could be some big positive epsilon, right? So making this kind of learning scheme a little confused, but overall it's quite closely follow that, right? And then switch to this, and it closely follow, right? Similar here. Similar. It's missing a little, but it's similar, right? So when we run this program, we had no idea about this, but only our assumption. Our assumption was this, and we are given this data, right? If our assumption is correct, and that's what we find, when actually data is generated by this one. So it's not exactly the same, but I think it should be very close enough. Right? So there is actually a red dot going on as a background. But let me... Actually, red dot represent this probability. But when you closely look at that, red dot here, move up here, and then collapse. That means when you have all the data here up to there, previously that was your calculation, right, on real time. But when I look back, this period could be categorized as 0, just one spike, right? So the probability is small. To the contrary, here, previously it sees that probability decreases fundamentally like this one, but the red dot goes all the way up to here and then bounce back. So when you have all the information, then you might think that, well, this is just single state. So hopefully, it would be nice if the smoothed probability like this one turns out to be something. This would be the best case, right? But I think this should be reasonably close. In this case, cyan color was like that, but red dot goes like that. Because you can hardly see that. Let me remove that. See, very small and very close. And it is not as deep as the previous case. Right? This is okay, and this is almost perfect, right? And this one, you consider, well, although it is state 1, it concludes that, well, this is a spike. We're missing a little here, but you capture this part. Okay. So this is regime switching model. This part is smoother. They calculate this one. It is very similar to previous smoothing algorithm of Kalman filter, when your estimation is completed there, you receive that converging parameter and then calculate smoothed probability and filtered probability from using this function. So this function receive final estimates and will return 1 and 2. So this 2. Okay. I copied this routine, have all codes written in this part, and it adds some more code. For example, if you compare this smoothing routine and the log likelihood routine, you can compare what are the differences. So this is the different part. See, these are the same, right? These are the same. This is the same. And in the meanwhile, we see that this is added, new, right? And this is the same. This is the same. So looks like what we've done here is we try to save this one plus right, this probability and this probability as this one, and this probability and this probability as this one. But these are all to evaluate this kind of probability. Right? So code is a little tricky, but as I said, when you save this as intermediate output, also these as intermediate output, and then starting from final estimate, so if your time t is cap t are the same, right? At time cap t, these two are the same. But if t is less than cap t minus cap t, then you are calculating this one backward. In this way. So a friend of mine wrote this part about 20 years ago and published it in a very decent journal, academic journal. But in terms of programming, not so much, right? So much. This, that, and this. Okay. So you can replicate this result by using this code. I call it smoother here. Different name, but same thing. Right? Same thing. I highlighted what's the difference between these two functions. This part, and that part. Okay. This is logistic transformation. So the output, our first probability was assumed to be 0.8. estimated to be 0.73. The second parameter, Q was 0.8, P was 0.9, and 0.87. These are significant. And beta 0 was 0.5, beta 1 was 1.5, and standard deviation was 0.25 in our data generating process. Right? So if we had, let's say, where is number of observation? Let's say number of observation is 1,000. So 1,000 quarter. Smoothing. Yeah. And somehow it all follows, right, very closely. But if you look at the output, where is my output? Point 0.8, 0.9, 0.5, 1.5, 1.24, 0.24. Right? More data, you have more accuracy. Right? Okay. So just in case you are interested in this code, and you don't want to type everything by yourself, then I can borrow you this code. Okay. And the applications, also our PDF file, you can't read this part, right? This is different file. As you can see, when you have this type of model, and if you have some scale, then sometimes it doesn't matter whether this one is known or unobserved. So let's say call it Y. This is vector. Now suppose this is a simple case of having this follows switching process, and this is sort of sensitivity coefficient parameter. So why they move, let's say, together, there is a common variation, right? Common variation. But some variable is more sensitive than the other. Right? Of course, there is a common variation coming out of this X, but they are idiosyncratic movement. Right? the structure could be more complicated if you introduce serial correlation here, and more complicated process than this one. But still, the idea is the same. But the problem is when you have these data, what's observed here, and your model, your assumption is in somehow there is some latent or common factor like X that is state dependent, like this one, or this could be also state dependent. Obviously, this is not observed, right? So in somehow, this one can be treated as a state equation, right? This one relates observed data and the state vector or state variable. So this is measurement equation. So it's sort of Kalman filter thing, right? Kalman filter. State space model. But the thing is similar here. T1 through cap T. When you iterate to handle this kind of state space model, because of the state, 4 possibilities, right? So Kalman filter prediction and update, those things, we have 4 versions every time. So things get more complicated, but basic idea is basically essentially the same as previous univariate case. As long as you can keep follow that calculation part of this type of probability, then you can calculate, collapse likelihood value into 1 and adding them up and maximize it. But that's beyond our level of undergraduate class. So just illustration here. I had a chance to collect this Japanese indicators that constitute a series of the index of coincident indicators. So these are coincident indicators. So by coincident, we mean that it's going to the same direction, right? So when you summarize this one into single series using some standardized method, that's the index of coincident indicators. So using that, you determine when is the peak and trough, and so on. But when you actually implement this type of model, where your assumption is that kind of business cycle up and down is created by this one, having this feature. So when this is positive, it's growing. When this is negative, then going down. Right? So when you actually did that, more complication, right? This is the part you barely identify, right? Rest of them is very complicated, but that's basically the way we elaborate this type of simple factor structure. So when we actually estimate that kind of model, you cast these sequence system of equations into this framework. But now you understand this framework, right? This is measurement equation. So this part corresponds to this one. And below you have state vector and its process. And it appears that there is a state dependence. those has to be appropriately defined. So when I try to transfer from my previous work at University of Alabama to Hanyang University, I wrote this algorithm with Professor Yu, and as you can see, there are a lot of I's and J's in this prediction, update, and forecast error variance expressions. And then magically a number shows up, and this is the probability I can calculate from there. So this shaded area is official Japanese business cycle recession. And given those data, this dark area graph is the probability that state being recession. Because this is model, so you can always generate a forecast, right? Forecast. And as I said, as I introduced, this kind of probability, transition probabilities, tells you kind of average duration. So duration means what is this average value? Once you enter to recession, how long? Once you enter in a recession, how long? That's the duration, right? So if you can calculate average duration, so average of these periods, right? Then when you actually are into recession, then you can make a educated guess that, well, our current recession could be on average 4 more quarters to go, something like that, right? Could be useful information. And the last comment. Before I make last comment, let me show you this slide. You can do a similar exercise. This is real GDP, seasonally not adjusted one, something like this one. This is seasonality trend, stochastic trend, and cycle. And we introduce this type of regime switching model into this growth rate, and some complication into state space framework, and estimation is done in somehow, and this was the one I showed you the other day, right? So 0.5 appears to be too high in this case to make decision, right? So if you draw some line at probably somewhere here 0.3, then it might be reasonable. It could be 0.3 or 0.35 or 0.4, depending upon your experience. You probably remember that the weather latest. Suppose you are at here. So this is the latest data, right? And it shows that recession started from here and ended right there, right? But when you're actually here, you don't see these shades. You see only this one. Because they wait until data is accumulated, right? Before they make official announcement that this is the end, right? So to find this start and end, if this has to be official, then you have to wait until this time, right? Suppose you are here and general election. So ruling party, opposition party, they will fight for current incumbent screwed up their economic policy, right? Foreign policy and so on. So suppose you are preparing your election, and in retrospect, recession ended, right? So economy started growing right here, right? But your opposition will say, well, look, we are in a recession, right? Probably they struggle over this period, right? So they feel it, well, the economy hasn't been good, right? But in fact, it is ended. But here, they have to wait until official announcement, right? But if you actually run that kind of program, switching model, we've seen that the probability is already showing see this trend. So this could be provide you some more information on real time. Right? Okay, this is all I have to say. Sorry that I take more time.